Hello everyone, I am Sarthak Pravin Gandhi from first year Information Technology. Today I will be presenting on the topic modulation techniques and data communication. This topic comes from unit 3 of our data communication course. So let's get started. Here is a quick look at what I will be covering today. We will start with what modulation is and why we need it. Then we will look at the different types: analog modulation, digital to analog conversion, analog to digital conversion, and digital to digital encoding. After that, I will show some real world applications, a comparison, and then wrap up with a conclusion. So, what exactly is modulation? In simple words, imagine you want to send a letter. You cannot just throw the letter into the air and expect it to reach someone. You need a vehicle like a postal van to carry it. In data communication, modulation works the same way. The message signal is your letter, and the carrier signal is the postal van. Modulation is the process of putting your message onto the carrier so it can travel long distances. The result is called modulated signal. Now, why do we even need modulation? There are four main reasons. First, antenna size. Low frequency signals need very large antennas to transmit. By shifting to higher frequencies using modulation, antenna size becomes small and practical. Second one is long distance. High frequency signals travel much farther with less energy loss. Third one is multiplexing. Modulation allows multiple users to share the same channel at the same time by using different carrier frequencies, like how many FM radio stations broadcast together without mixing. Fourth one is noise immunity. Some modulation techniques handle noise much better than others, giving cleaner signals at the receiver. Modulation techniques are broadly divided into three categories. First is analog modulation, where both the message and carrier are analog signals. This includes AM, FM, and PM. Second is digital to analog conversion, where digital data is sent over an analog channel. This includes ASK, FSK, PSK, and QAM. Third is analog to digital conversion, where analog signals like voice are converted to digital form. This includes PCM and delta modulation. There is also digital to digital encoding like NRZ and Manchester, which I will cover briefly. Let us look at analog modulation. There are three types. In amplitude modulation or AM, the amplitude of the carrier signal changes according to the message. The frequency stays the same. AM is simple but picks up a lot of noise. You hear it on AM radio stations. In frequency modulation or FM, the frequency of the carrier changes according to the message. The amplitude stays the same. FM is much better at handling noise, that is why music sounds clearer on FM radio compared to AM. In phase modulation or PM, the phase of the carrier signal changes. This is less common in everyday broadcasting, but it forms the basis for digital phase shift keying, which we will see next. Now, let us talk about sending digital data over an analog channel. The first two techniques are ASK and FSK. In ASK, amplitude shift gain, a binary 1 is sent as a high amplitude signal and a binary 0 is sent as low or no signal. It is simple but very sensitive to noise. In FSK, frequency shift gain, a binary 1 uses a higher frequency and a binary 0 uses a lower frequency. FSK is more reliable than ASK. You will find FSK used in Bluetooth communication and older modems. Think of it like this: ASK is like turning a light on and off, while FSK is like switching between two different colored lights. The next two techniques are more advanced and widely used today. PSK, phase shift keying, changes the phase of the carrier to represent bits. In BPSK, we use two phase values, 0 degrees for 0 and 180 degrees for 1, giving us 1 bit per symbol. In QPSK, we use four phase values, giving us 2 bits per symbol. PSK has excellent noise performance and is used in Wi-Fi and satellite communication. QAM, quadrature amplitude modulation, is the most powerful technique. It changes both amplitude and phase at the same time. 16 QAM gives 4 bits per symbol, 64 QAM gives 6 bits per symbol, and 256 QAM gives 8 bits per symbol. More bits per symbol means more data in the same bandwidth. This is exactly why 4G LTE, Wi-Fi 5 and Wi-Fi 6 all use QAM. They need very high speeds. Now let us look at how analog signals like voice are converted to digital form. The most important technique here is PCM, pulse code modulation. It works in three steps. Step 1 is sampling. We measure the analog signal at regular time intervals. According to the Nyquist theorem, we must sample at least twice the highest frequency of the signal. For human, twice with a maximum frequency of 4000 Hz, we sample at 8000 times per second. Step 2 is quantization. Each simple value is rounded off to the nearest value from a fixed set of levels. Step 3 is encoding. Each quantized value is converted into binary bits with 8 bits per sample and 8000 samples per second. We get 64 kilobits per second, which is the standard for one voice call. There is also delta modulation, which is a simple version. It stores only one bit per sample, just whether the signal went up or down. It uses less bandwidth but can distort if the signal changes too fast. Quickly on digital to digital encoding, this is about representing digital bits as digital voltage signals on a wire. NRZL is the simplest. High voltage is 1, low voltage is 0. Easy but has synchronization problems. NRZI improves this by making a voltage change represent 1 and no change represent a 0. Manchester encoding is the most reliable. Every single bit has a voltage transition in the middle. This built-in transition helps the receiver stays in sync with the center. Ethernet uses Manchester encoding for exactly this reason. Here is a quick comparison of all the techniques we covered. You can see that as we move from ASK to FSK to PSK to QAM, both the number of bits per symbol and bandwidth efficiency increase. QAM gives the highest efficiency but needs a cleaner signal. PCM and Manchester encoding are preferred where reliability matters more than speed. The right choice always depends on the application, its distance, noise level, and required data rate. So, to summarize, modulation is the foundation of all communication systems. Analog modulation like AM and FM has been used for decades in broadcasting. Digital to analog techniques like PSK and QAM now power our Wi-Fi and mobile networks. PCM is how voice is digitized for phone calls, and line coding techniques like Manchester encoding keep our wired network synchronized. Every wireless signal you send or receive, whether a WhatsApp message, a phone call, or a YouTube video, has been modulated somewhere along the way. Before I open the floor for questions, here are three important questions from these topics along with their answers for quick revision. Question 1. What is the difference between AM and FM? In AM, amplitude changes, in FM, frequency changes. FM is more noise resistant. Question 2. Why is QAM more efficient? Because it changes both amplitude and phase together, allowing more bits per symbol, up to 8 bits and 256 QAM. Question 3. What are the three steps of PCM? Sampling, quantization, and encoding. Sampling must follow the Nyquist rule at least twice the highest frequency. Thank you for listening. I am now open for any questions.